Hello everyone, welcome you all in the course of renewable energy resources. Today we will discuss about thermoelectric generators. To better understand this topic, first of all we will discuss about the direct conversion devices. For that we had taken an example that how do we get electricity in a power plant. Here we have fuel which when burnt gives out thermal energy which then goes to our power plant that is connected with a turbine from where we generate mechanical work. So as we have thermal energy in the power plant, we get mechanical work because of the motion of rotating turbine. And this turbine is again connected to the generator whereby we get electrical output or electrical energy. So what we are having that thermal energy is converted into mechanical and then to electrical, and in this process we are having lot of equipments as boiler in the turbines from thermal to mechanical, and then again we have generator from mechanical to electrical direct conversion. So this is what we call traditional power generation. So this is from fuel in direct conversion. However, what we have a source of thermal energy and which is directly converted to electrical energy. So this device can be of several type, and what we are going to discuss today is one of those. So once again, what we mean by direct conversion device is that we have a source of heat, a source of thermal energy with us. For example, some waste heat which we want to utilize that waste heat and the energy trapped in that waste heat to generate additional electricity. So these direct conversion devices offer one means or one type of means by which we can convert the thermal energy directly to electrical energy. So today we'll discuss about one such type of direct conversion device which is called thermoelectric generator, which is often called as TEG, and to better understand it we will study its effect, that is thermoelectric effect. Thermoelectric effect is a phenomena by which thermal energy can be directly converted to electrical energy without any moving part or working fluids like what we need in traditional power plant. This directly word is very crucial here. Now let us see why is this happening and what is there inside a thermoelectric device which is leading to this phenomena. So to understand that, what we will do is we will go back in history a little bit and talk about something which is related to this effect. So in this, first we have Sir Thomas John Seebeck. In 1820, he accidentally found if we took a metal bar and if there is a temperature gradient across that metal bar, then he was able to show that there is actually a voltage that existed between the two ends of the bar. So this is what Seebeck found at the beginning as an accident, and he worked on this finding a lot. Then finally, what we know Seebeck effect today is that if you have two dissimilar materials that are used to make two junctions and one of them is kept at an elevated temperature and the other one is kept at a low temperature, then you will get we get an EMF for a voltage across the materials. Now hand in hand, what happened was Peltier effect. Peltier effect many times is said to be just the opposite, which means that if a direct current flows through a pair of junctions or dissimilar material, then a temperature difference is created across the two junctions, resulting in heat flow. Again, I repeat, what it means is if you have again two materials A and B. In 1851, Lord Kelvin discovered that when current flows through the unequally heated conductor, heat is evolved or absorbed through the conductor. Now we will discuss these effects in detail. So in this first is Seebeck effect, which states that if two dissimilar material are used to make two junctions, one of which is heated and the other cooled, a resultant electromotive force is generated between the materials. And the most common application that we use as engineer is in the thermocouple. That in thermocouple we measure temperature using Seebeck effect. Now, let us take an example. We'll consider two dissimilar material, one at temperature T1 and the other at temperature T2, and we are heating it up. The other end is maintained at lower temperature. then what we see that if we measure an EMF or voltage, it shows that current is flowing through it. Seebeck also showed that if this EMF is directly proportional to the temperature coefficient delta T and the proportionality constant, and named it as Seebeck coefficient. So alpha A minus B is the Seebeck coefficient, which is often denoted as alpha, which is used to denote Seebeck coefficient from A to B, which is proportionally constant and relates the amount of voltage that we are going to get, or the EMF that we are going to create due to the temperature difference delta T. This is Seebeck effect. Next in the list is the Peltier effect. Peltier effect many times is said to be just the opposite, which means that if a direct current flows through a pair of junctions of dissimilar materials, then a temperature difference is created across the two junctions, resulting in heat flow. Again, I repeat, what it means is if you have again two materials A and B. So this is how. As you can see in the figure, we had taken two material. One is of N type and another is of P type. Let take N type as A material and P type as B material. As we had taken two dissimilar material, the amount of heat, and this is over and above Joule heating, because whenever you have a current flow, you will have Joule heating, but there is an amount of heat over and above Joule heat, which has to be removed or absorbed at the junction to keep them at the same temperature, at constant temperature, and this additional heat which is to be removed over and above Joule heat is known as Peltier heat and is given in this expression. As you can see, it is denoted by Q, which is equal to pi A minus pi B times current, and here again this pi A minus B is known as Peltier coefficient. So therefore, on one hand we have a definition of Seebeck effect and the definition of Seebeck coefficient. Here we have the definition of Peltier coefficient, which relates the amount of Peltier heat that is generated due to current flow across a junction of dissimilar material, and that relate it to the heat that is generated is related to the current that is flowing through the circuit that is formed because or by these two dissimilar material, and the two are related by Peltier coefficient. Now coming to the next, that is Thomson effect. Thomson effect states that any current carrying conductor with a temperature difference between the 2 points will either absorb or emit heat, depends on the type of material used. It states that heat is absorbed or produced when a current flows in material with a certain temperature gradient. The heat is proportional to both the electric current and the temperature gradient. This is known as Thomson effect. Thomson effect is further divided into three types: positive Thomson effect, negative Thomson effect, and nil Thomson effect. Positive Thomson effect states that current flows from lower T to high T, heat is absorbed throughout the conductor. Negative Thomson effect states that when current flows from lower T to high T, heat is liberated throughout the conductor, and the nil Thomson effect states that when current flows from high T to low T or low T to high T, heat is neither liberated nor absorbed. You can see its example also. Next is the thermoelectric material. The material which we used in thermoelectric devices should possess three qualities. It has large Seebeck coefficient, it must have high electrical conductivity, it must have low thermal conductivity. The example of thermoelectric materials are bismuth telluride, lead telluride, silicon germanium, bismuth, antimony. Next, we will study about the principal construction of thermoelectric power generation. The thermoelectric power generator based on the principle of Seebeck effect, that when the junction of two different materials are maintained at different temperature, the EMF is produced in the circuit. In order to select material and design a thermoelectric generator, one needs to start with a general understanding of thermoelectric effect. In thermoelectric material, there are free carriers which carry both charge and heat. Perhaps the simple example is a gas of charged particles. If a gas is placed in a box within a temperature gradient where one side is cold and the other is hot, the gas molecule at the hot end will move faster than those at the cold end. The faster hot molecules will diffuse further than the cold molecules, and so there will be a net buildup of molecules at the cold end. The density gradient will cause the molecules to diffuse back to the hot end. In the steady state, the effect of the density gradient will exactly counteract the effect of the temperature gradient, so there is no net flow of molecules. If the molecules are charged, the buildup of charge at the cold end will also produce a repulsive electrostatic force to push the charges back to the hot end. So this is about principal construction of thermoelectric generators. Now its advantages. TEGs are environment friendly, they recycle wasted heat energy, they are reliable source of energy, their scalability is good, they have low production cost, they are silent in operation, they are simple, compact and safe. Next, the disadvantages of TEGs: it has low energy conversion efficiency, it requires a relatively constant heat source, it has slow technology progression. The applications of TEGs are as follows. The applications are thermoelectric generator, cooling computers, drink coolers, recharging devices, space probes, solar power, low power remote control system, nuclear power station, automotive TEGs. So this is all about TEGs. Thank you.